let's see a couple more things, right? So something that came up here was that we had, at this point here, right, we actually, we had to figure out how to compute this, P of plus, right? And then we figured out how to do it, but there's actually, a couple of general rules behind that you want to know, right? And those rules, they're very simple, but incredibly useful. They're the product rule and the sum rule. And you may remember this from Stats 101 or not. In any case, let's go over it. So the product rule is a way to compute the probability that two events happen, A and B. And it's just what we've seen in a number of instances already, is that P of A and B is P of A given B times P of B, or alternatively, it's P of B given A times P of A. Okay? The probability that A and B happens is the probability that A happens, and then B happens, given that you know that A happened. Okay? The second one is the sum rule. The sum rule, so the product rule is the probability of a conjunction of things, A and B. The sum rule is the probability of a disjunction of things. Where's the probability that A or B happens? Okay? So the probability that A or B happens is the probability of A plus the probability of B, right, minus the probability of the intersection. Why did I subtract the probability of the intersection?
It's counted twice.
Because it's counted twice when you add them up. Okay, so doing this with that old stalwart, the Venn diagram, right? Here's what we have, right? This is A, this is B, right? So P of A, let's say we have uniform distribution over the plane here. P of A is the area of this ellipse. P of B is the area of this ellipse. When I add the two, this area here got counted twice. Okay, this is A and B, right? So now I have to subtract it once so that I have the right result. Okay, everybody agree? Okay, very good. So these two rules are two of the most useful things you can know in probability. It's amazing how much basically just falls out of them. One of the things that falls out of them that's actually what we were sort of like using in a very simple form just now in the cancer example is the theorem of total probability. Okay, and the theorem of total probability is again best illustrated with a little Venn diagram. And this is the following. Again, let's suppose that the plane here of the tablet is my event space. And let's say we have a bunch of events that partition the space. Let's call this, A1, A2, A3, A4, A5, A6. Okay? So one of these is guaranteed to happen, and no two of them happen at the same time. Okay? So mutually exclusive and exhaustive outcomes. Okay? And now I have another event that I'm interested in, and that's B. Okay? And again, P of B is the area of this ellipse. Okay? And now what the theorem of total probability does for us is it allows us to compute the probability of B as a function of two things. The probability of each of the A's, so P of A1, P of A2, etc., and the probability of B conditioned on each one of those. Okay? So the A's partition the set of all outcomes into some distinct things, and now what I want to know is the probability of B as a function of how often each one of those happens, each of the A's, and how often B happens when one of those is true. Okay? And so here's this formal statement of this. So what is P of B? Right? P of B is the sum over all the A's of the probability of A times probability of B given A. Okay? Why is this the case? Right? Well, clearly the total area of B is the sum of these sectors, right? You agree? And what is each one of these sectors, right? This sector here is A1 and B, right? A1 and B. You agree? And this sector here is what? A6 and B, right? So P of B, let me write this here, right? P of B is equal to what? P of A1 and B, right? Plus P of A6 and B. You agree? This is very simple. This is just decomposing this orange into its segments. Okay? Very good. But now I can apply my definition of conditional probability or product rule, right? And what is P of A1 and B? It's P of A1 times P of B given A, right? It's the probability. So okay, let me write that down. So P of A1 and B, right, is equal to P of A1, right, times P of B given A1, right? Everybody agree? And the same thing holds for everybody. So notice, right? At this point, we have our theorem, right? It's just the sum over all the A's of P of A, of P of that A times P of B given that A. Okay? And if we go back to the Venn diagram, why is this the case, right? Well, P of A1 is this whole segment, right? Assuming that the P of the whole space is 1, right? But I'm only interested in this fraction of the segment, right? So P of A1 tells me the size of the big segment, and then and then this is the size of the smallest segment where B holds, and it's the sum of those that I'm interested in. Okay? Everybody follow this? Why is this so useful and important? Because often it's very hard to just flat out compute the probability of something. This is a little bit like the probabilistic analog of reasoning by cases, right? Think about the following, right? What are your chances of getting run over by a car if you cross the street? This is a little hard to figure out, right? But now let me ask you another question, right? What are your chances of getting run over by a car if you cross the street when the light is green for you? Well, that should be low, right? Unless there's some crazy driver out there, right? If the light is green, then you can go, right? And now let me ask you the other question, right? You're at a busy intersection, right? Picture yourself like in the middle of Manhattan with all that traffic rushing through, and people there are not nice like they're here in Seattle. They will not slow down for you, right? So what are the probabilities of getting run over by a car if the light for you is red? Well, that one is pretty high, right? Because they are rushing by. If you're just walking to the intersection with the red light, you might be in trouble, okay? So this is what the A's are. Here, the light is red, the light is green. And B is the probability that you get run over. The probability that you get run over is totally different depending on whether it's green or whether it's red. Okay? And so what I'm doing here is I'm going to compute the probability. So what is the probability that it's green? What is the probability that it's red? What is the probability that you get run over given that it's green? And what is the probability that you get run over given that it's red? And then the sum of that is the probability that you get run over. Okay? Questions? Okay, very good. So these are just a few useful probability things to know.